go. Okay. Audio's there. Good, good. All right, so let's go ahead and start to discuss. So definitely as we go through these optimization problems, a lot of them are kind of geometric. So we can get used to some of those formulas and whatnot. But as you read through, there might be some more kind of like business oriented, trying to sell items, purchase or make rentals on the hotel, like I mentioned. Okay. We can start to see those, and likewise in like physics and chemistry, optimizing there. But let's look at this case here. Another common problem. Where was it? Here, I think. Okay, let's check out this one. Kind of like I mentioned in our example yesterday. Let's check this out. Okay, so let me switch over to the .cam. We should all be able to see that. Chat function is there in case we have questions along the way or can't read or see something. But here we go. All right, so here we are. The .cam should be visible. Audio should still be on me. Good, good, wonderful. All right, so here we are. So in section 4.7, right, our optimization, trying to find the maximum, minimum for some application, some physical quantity many times over. All right, that's kind of a little bit fuzzy there, but as I start to write more, I think it'll be able to focus in. But let's check out this problem from the text, number 16, on page 337. Again, this is section 4.7, and it says here that a rectangular storage container with an open top is to have a volume of 10 meters cubed. Okay, 10 cubic meters. The length of its base is twice its width. Material for the base costs $10 per square meter. Material for the sides costs $10 or $6 per square meter. Find the cost of materials for the cheapest such container. Let me zoom in, let you guys see that problem as it's written. Okay, slide that up. There we are. So number 16 here. This is a rectangular storage container. Again, a common aspect, right? We have this box with an open top. That's going to have a volume of 10 cubic meters. All right, so it's basically like a big dumpster. All right, the length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. Right? We're trying to minimize that cost. All right, so with that said, let me write out some of that information, and then we can start to organize our equation, our formula, take our derivative, find, in this case, that minimum, right? All right, so in this case, we want to build up this rectangular storage container, right? So we want to construct, we want to build a rectangular storage container with no lid, right? So that means we don't have to worry about using up any materials and having to pay for a lid, a top to it. Okay, and then, right, that container must have volume (10 cubic meters). The length of that base will be twice the width. Okay. And then now coming into the money side of it, material for the base, right? Because you want to have a sturdy base that's going to be able to hold that weight. Costs $10 per square meter. Okay. And then material. I know always with these problems, a lot of language, a lot of writing as we open it up. A material for the sides. Costs $6 per square meter. All right, so the sides don't have to be as thick. So now what we want to do, we want to find the cost of materials for the cheapest. All right, well, I'm looking at their language here. For the cheapest such container. Right, and so again, we're going to draw a picture. We're going to do some labeling here, but at this tail end, what we kind of see that we want to find the cost of materials. That's the cheapest. That's that bubble. Okay. So that means that we want to minimize. We want to find the smallest possible the cost. Okay. So trying to keep track of what we're working on, what we're trying to optimize, find the max or min for. Okay. So we need to build up later, right, an equation for that cost. And then we're going to have to take its derivative, right? So as we go through, let me start to label, draw some information a little bit, and then we'll kind of dive back into it, right? So what we kind of see is not worried about necessarily the construction of it, right? We're not cutting any corners out like we did in our example yesterday, but we're just kind of more or less thinking we have this rectangular container, no lid, okay? That we have a certain cost for the base. $10 per square meter. And then for the sides, I'll go this way, I guess. We have another cost, right? And for how many sides are there? 1, 2, 3, there's 4 sides, right? And since we're not making a lid or whatnot, there's only one base, right? We can bring in those dimensions in our next phase, okay? But just thinking about this, I'm trying to minimize that cost, right? So in this case, my total cost for building up that box there, that rectangular container, our cost for the base plus the cost for our 4 sides. Right, and so again, that might be a little simplistic, but just so we can kind of get an idea overall what we're dealing with, right? Before I worry about trying to jump into equations, variables, all this and that, if I just build up this relationship, and that's what I'm trying to make as small as possible, that cost, okay? And so as we start to go through it, right, as we start to look at these components, our total cost, I'll call it C, right? That's going to be equal to the cost for the base. And as we start to go through for that base, I'm going to zoom out just a little bit here if I can, keep that visible, right? The cost for that base, let me see if this window will scroll down. There we go, better. All right. So now, for that cost of the base, it was $10 per square meter, right? Square meter, meter squared as an area. So it's going to be our cost here, $10 times the area of the base, depending on how big that base is, right? Like we kind of saw yesterday how wide or small I make that. If I make it a really narrow base, but a tall container to hold all that volume, a little bit less cost. Or if I make it a wider base, maybe it'll be stronger, less height, still containing that 10 meters, right? Or 10 cubic meters of volume. And then for the cost of the sides, I know a lot of green here showing up, right? We're going to get here this $6 times, and we have to think about this one a little bit more, right? Our area of our 4 sides. I swap between the number and the written word for, but there we are, right? But we can kind of start to identify this idea, right? So slowly but surely, letting these numbers, like the variables, creep in, right? Because what's happening at the end of the day, we want these areas for our base for the sides to depend on just one variable, right? That's like the key part, like our related rates. Since we're going to be taking this derivative, we want just one variable showing up. Okay? So how are we going to get those components? So let's think about, again, that image, right? Start to put this together. So as I start to work on that, here, it's a little high on that paper, but that's all right. So here's our rectangular container, okay? And so for our base here, we have our length and our width, and of course for the sides, we're gonna have that height, right? And so already in our statement, we are told already that the base has length twice the width, right? So already we can start to replace that length is going to be 2 times W. Right, and again, that was a statement in the problem itself. All right. So we're starting to get that down. All right. But now, what else can I do? How can I get rid of this height? Okay. So if I'm trying to get all this information kind of condensed down to one variable, in this case, W seems to be like the winning candidate so far. If I want to get just one variable, let me cycle back up here. That when we were talking about that rectangular container, it mentioned that the container has to have a volume of 10 meters cubed, okay? And so what we can start to see is that we have a constraint, right? A constraint, like a restraint, right? Something that's going to limit our possible values, our choices in our process. We have a constraint, right? The volume of this box must be 10 cubic meters, right? It's fixed, like just like if you're producing some item, right? If you're filling bottles of soda, it has, that container you're dealing with has to hold a certain amount of volume to sell, right? So there's this constraint, this other factor that has to come in as we start to go through the overall discussion of our problem. Okay. All right. So we have this constraint, and this is what allows us, the constraint, this will allow us to rewrite our variables in terms of a single variable, right? So all those other variables we can condense down to a single, right? And so for us, the volume, length times width times height. I'm going to shift this up, okay? So as we start to work our way down, right? Well, the length, we had talked about it already. That was supposed to be 2 times the width, right? And then, of course, our width there, and then our height. So just taking a second here. Not too bad. Multiply those together. All multiplications here. But now we're trying to get rid of one of these variables. right? We have W's here. So if I get this H in terms of W, that'd be great. And so with that constraint, that volume has to be 10 or 10 cubic meters. I'll leave out the units for now, equaling 2W squared times H. And so if we divide both sides by the 2W squared, we know the width can't be 0. We're not dividing by 0. A width of 0 would mean, right, there's no base to it. That kind of closed interval discussion yesterday. What's the smallest W can be? What's the biggest W can be? That idea, right? So now, if we divide by the 2 there, or 2W squared, sorry, H by itself, simplifying here, we get H is 5 over W squared. Sorry. So now we have the height of that box in terms of the width of its base, W, right? And the length we had done earlier, I'll say go back up here, 2W. So for that volume, we've gotten all the terms of W. So that way the volume will always be 10 cubic meters. So now we can come back to our discussion about the cost. We can start to label in our components here and identify. Okay, so let's, again, redraw. Hope we're clear here. Let me know if you have any questions or if I need to slow down. Okay. So now, going through it, let me draw my box here a little bit lower. That rectangular container. Okay. And so for that base, we talked about it. The length was 2W, the width W. I know not drawn to scale. Okay, so there's that base. And now let's think about our size, right? So the height, we had talked about it, was 5 over W squared, right? That was our last step. Getting that constraint, the volume, to help identify how H is going to be in terms of W. I'm going to label here length. Okay. So when I start to look at our different sides, well, that wall, okay, let's think about these, the sides. Right, this side here, we're going to have one side be, I know it's again not drawn to scale here, W, with this height 5 over W squared. Right, so that's this wall. And then of course on the back wall as well, or we go left and right sides, that's going to be the same. So we have 2 of these, and then maybe I'll make it a different color, that if we have the front and the back wall, right, the height is still 5 over W squared, but now that base component is your length, which was 2W, right? And then again, the front and the back wall, mimic that image, right? We can see these different pieces, right? Again, thinking about having to build that up, sorry. I know it's a little small and washed out. All right, let me see if the light turns on. Does anything better? Maybe, maybe not. Let's see here. Okay, but you can see as we build up the box, that container, and really think of like construction side. Okay, I need a piece for the base, then my 4 sides around, I need to build those up, right? To accommodate, to incorporate all the cost. right? So then for our work here, our total cost, that's going to be equal to our base, right? Plus the cost for our 4 sides, right? And so as we start to deal with those 4 sides, we have 2 of this form, 2 of this form, right? So then as I start to build this up for that base, $10 times, now the area of the base, 2W times W, right? The length times width, plus, and I'm going to need some more space here, for these 2 sides, okay, there's 2 of them of $6. There's my cost of these 2 sides, right? The sides here, the width times the height, like so. And then plus another 2, $6 for the sides. But now this one is going to have the length, 2W, times the height, 5W squared. And I'll kind of put this as a single line on my next page, but just trying to see kind of with those images and where these costs are coming, right? There's 2 of these sides, $6 times the area. 2 of these sides, $6 times the area of those sides. Okay, and then we can draw arrows like these 2 are for this guy, these 2 are for this one, and then of course our base, that one a little more nicely color coded. Okay, but now, as I had mentioned, we had taken that cost and we've boiled it down to a single variable. Okay, so for my cost function, let me write it in black this time. Our cost equation, zooming out, it's a little small today. All right, again, let me put here 10 times 2W times W, we'll multiply that all out, plus 2 times $6 times W times 5 over W squared, plus 2 times $6 times 2W times 5 over W squared. All right, so if I start to multiply 2, 10 times 2, 20, W times W, W squared, plus here 2 times 6 is 12 times 5, right? Or 5 times 6 is 30 times 2, we get 30. W times a 5 over W squared, right? W squared in denominator, one of those cancels, we get 30 over W. Similar over here, right? One of those W's cancels, so we're gonna get another W in denominator. 2 times 6 is 12 times 2, 24. 24 times 5. Okay, we get 120, right? 5 times 6 is 30 times 4. 30 times 4, 120. So in total here, now I can zoom and make that a little bigger to see for everybody. There we go. That our cost, 20 times W squared, plus adding these 150 over W. All right, so depending on how wide we make that base, right, the length will be directly tied to it. The length of the base is going to be twice that quantity of W we find. The height, 5 over that W squared. All right, again, with our values, we know W can't equal 0. You get a 0 in the denominator here. No volume in that box, right? Then we can also start to address how large it is, but working from this stage, we're going to move forward. So there's our cost equation, okay? And so now, from here, remember, we want to minimize the cost. So with our discussion in chapter 4, 4.1. That means we're going to differentiate, take our derivative, and look for our critical numbers. Okay. And then through, whether it be first derivative test, second derivative test, other means, we can look for that max, min. Okay. Or determine those critical numbers, our maximum or minimum. All right, so let's go. So here's our function, our equation. Let me rewrite that. 150 over w, 150 times w negative 1, right? Taking our derivative, power rule. Negative 2 there, right? Negative 1 minus 1 makes a negative 2 exponent. Okay. Middle term, 60. 30, there, oh, you're right, 60. Thank you very much for that, Mr. Dillon. That should be a 60. I did my 5 times 6 times 2. That should be 60 there. Arithmetic's out the door. This is 180. 180. 180. There we go. Thank you very much. That would have thrown off my calculation later. Better. 5 times 6, 30 times a 2. I forgot to double 60 there. Very good. This one I did correctly. Let's hope. 5 times 6, 30 times 4, 120. 24 times there. Yeah, looks good. Good. Thank you for that. Differentiating there. Better. Okay. Make sure I got my power rule right. So there we are. So there's our derivative, right? If I rewrite this in more standard notation without that negative exponent, 40w minus 180 over w squared. And now for our critical numbers, right? We want that derivative to equal 0. So setting that derivative equal to 0, to find our critical number, what width is going to produce is going to kind of help us locate a possibility for a maximum or minimum or true or minimum. Solving here, again, we're assuming w can't be 0. So if I multiply both sides by that w squared, clearing the denominator, move that work up here, we're going to get 40w cubed minus 180 is equal to 0. Depending on what I want to solve, we can start to isolate that w cubed, right? Because I probably don't want to have to deal with factoring a cubic. Dividing by 40 on both sides. 180 over 40, right? The zeros go away. Dividing by 2. W cubed is going to be 9 halves. Double check my arithmetic. You got me worried. Okay, and again, as in real life, we're probably going to get some weird decimal answers, some weird quantity. But for now, our value for W, this cube root of 9 halves. I can bring out my calculator if you want to see a decimal. I'm not going to be that worried about it, truthfully, but let's check it out. 9 halves. Should I write this? 9 divided by 2, 4.5, raised to the 1/3 power. Taking that cube root, boom. And so in that case, I'm getting this decimal about 1.65 if I round 2 decimal places, okay? But again, truthfully, when it comes into it, right, we're mathematically going to want to solve exactly, but for the engineers, physics, then we'll start to bring out that calculator, right? And this is in terms of meters, okay? So with that said, we have this critical number. Only one critical number showed up. That cube root is a one-to-one function, no possibilities. And so typically, and with many of these examples we'll start to see, we only get one critical number, right? And so lazily, typically, we will assume that the one critical number will automatically be our desired result, right? That's going to be the value that's going to maximize or minimize without even really double checking, okay? I think we got one, no, we did get two yesterday with that 3 halves. Okay, I was thinking about my example. But, right, if we get just one critical number, we're going to assume automatically that that's going to be the one that's going to give us our optimized quantity, whether it be the minimum cost in this case, maximum volume, whatever it is, okay? But it's always a good habit for us to check. We should check or verify, right? Make sure that that critical number is indeed giving us the minimum cost, okay? So that's when it comes into our number line, our different possible values for the width, our derivative, we'll check up there, right? So our one critical number, 1.65, where that derivative is 0. So let's check on either side. So I'll use 1 and 2. Sorry. That should actually, be my cube root of 9 halves. There we go. Sorry. Trying to move too fast. I'm getting lazy there. There we go. Better. Right. So again, automatically, I'm going to assume that that's going to be my minimum for that cost. But let's make sure for our derivative that we're getting decreasing to increasing, from negative to positive, that change, right? So for our derivative, it looked like 40w minus 180 over w squared, right? So when that width is 1, our derivative, 40 times 1 minus 180 divided by 1 squared, right, which again looks like 40 minus 180, which of course is negative. Decreasing there. Sorry, I saw that up. Okay. Again, with these values, it's not that difficult to compute. Not really much factoring here. So then when w equals 2, (40 times 2 is 80. 180 minus, all right, 180 over 2 squared, 4. Okay. And doing that, we can double check. That's going to be 80 minus 180 divided by 4, right? We talked about up here that 9 halves, 4.5, we tack on a 0 or multiply by 10. That should come out to, I think, 45. Double check my arithmetic. And in that case, right, positive though. That's the big concern. And so definitely with that first derivative test, at that critical number, we're dropping from a, right, decreasing, dropping. Then after that critical number, we're increasing. So we're dropping down to that minimum, curving back up. So that just verifies for us. Again, a lot of times we just bypass that, but it's something interesting and definitely worthwhile to consider. So in that case, that's our verification. Indeed, that critical number, locates a minimum for us with that first derivative test. Okay. So in this case, going back to the problem, the question asks, find the costs of the materials, right? So here, my original question, just to make sure I'm answering in a problem, we want to find the cost of the materials for the cheapest container. Right, so I found that width that's going to produce the cheapest, right? But we actually want to find the cost. So in that case, going back to our cost function, our cost equation that we had differentiated, there was my total cost that we computed, right? I want to go back to that. So my actual cost then, 20W squared plus 180 over W, right? So there's my cost. So when I plug in that critical number, and again, that's probably where I'm going to bring in my calculator, because it is going to be something strange. We could round, or since I do have my calculator, I'll keep the full radical expression, but we can round and put that 1.65 there. But if I was to compute, let me type this in real quick. So that's going to be the cube root of 9/2 squared inside the first one, 20 times that, plus 180 divided by the 9/2 raised to the 1/3 power, cube root there. Let's see here, boom, boom. All right, so there's how I typed it into my calculator. 20 times that 9/2 inside the cube root raised to the second power squared, right? So my 20W squared plus 180 over that W, that 9/2 to the 1/3 power, and it's kind of a glare. All right, and we can round that 1.65 and see how that compares. But doing so, I got 163.54, so approximately $163.54. Okay. So that's going to be as cheap as we can build that container. All right, and there we go, pretty much spot on. If I use that 1.65 to round, that cube root of 9/2, right? It comes out same up to 3 decimal places, which is nice. Okay. But again, just finally, that last part, just making sure we're answering. It didn't. Some problems ask you what's the final dimensions, and you can give the width, the length, the height. In this case, they want to know what the cost is that you're actually paying. Okay. And then kind of scaling back, tying back into what we would have seen yesterday, right? If we were to graph that cost function, sketch that out, right? We would see with that graph that we'd have a minimum for that curve with that value W. Again, it might be hard to read off that graph precisely, but we can kind of estimate like so as well. And that graph yesterday, when we're trying to find that maximum volume, right? If you graph that function or even its derivative to see where that max will occur, you can see those on our graphs as well, kind of tying back into 4.5, how we were using that derivative discussion to locate maximums, minimums, right? That same kind of work now, but now having a more physical meaning for what that curve is representing for us. The different volumes we might achieve, the different costs we might have to pay depending on how we alter that variable, in this case, our width for that box we're building. Okay? All right. And so depending on what relationship we're trying to build, right? A lot of these problems are like with these costs that we're dealing with, these geometric, we're trying to enclose some field, build a container, right? We also have some cones. I think some of the examples we can see, right? We can start to construct these equations whose derivatives, they're critical numbers, right? Can help us locate where a maximum minimum occurs. So just a matter of building that equation depending on one variable so we can maximize, minimize, optimize those quantities. Okay? All right. And again, if you have any questions on those, let me know. We haven't covered too many examples. We'll try to fill in some more as we go along. I said that for the curve sketching as well. I need to make sure I do that. All right. But with that said, what I do want to do though is introduce with these last couple minutes this final topic for our course. Okay. And so as we go on, 4.8 is kind of fundamental method for programming, solving these problems using the derivative. Okay, solving equations, solving polynomial equations, so on, using that derivative. Okay, but we're going to bypass that, and then in section 4.9, that leads us into chapter 5. We're going to talk about antiderivatives and in chapter 5, right, our integrals. Okay, so what we're really going to be focused on as we finish out, okay, these last bits of discussion, okay, is that here, right, in chapter 3, we learned how to take a derivative, right? We said, okay, if I take that derivative of x squared, I know my derivative is going to be 2x. Or likewise, if I took the derivative of, say, 8 sine of x, my derivative would be 8 cosine of x, right? That coefficient sticks around, derivative of the sine becomes cosine, so on. So now, in 4.9 and leading into chapter 5, right, anti-derivatives, right, anti, kind of the opposite, right? Now, we want to go backwards. Right? Our question becomes, right, what function, what equation has a derivative equal to whatever it might be? Let this up. Right? So our discussion is like, okay, for example, if my f prime is equal to 2x, right? That's my derivative. What does my original function look like? Okay, so here's our derivative. We're trying to think about, okay, well, what does my original function, my original equation, look like? And so just kind of cycling through notations, thinking here, right? We're kind of identifying that, okay, the derivative of something, f here, right? Or question mark, that needs to be equal to 2x, right? So what is that function? What function can I put there such that its derivative looks like 2x, right? Such that its derivative looks like sine, cosine, whatever it might be, right? Another one might be like the derivative of something needs to be equal to the secant squared of x. All right, just kind of thinking back to some of our differentiation rules. So now we're going to start to work in that direction. Given some function and expression, what is the original function that we can use? So that way, when we do our check, if I was to take derivative of that, I would get exactly that derivative answer. Okay, so that's what we're going to be working on as we finish this out, that work in chapter 5. And so in chapter 5, if you look at it, sections 5.1, 5.2, I think, all right? They bring in some notation, but it lays the groundwork for it, right? Stuff that we don't necessarily use rigorously moving forward, right? So just like when we did derivatives, I made you guys go through all that limit work, right? So section 5.1, 5.2, that's what they're dealing with, okay? They're making you go through the limits. So I'm not going to kind of, especially with our time, I'm not going to dwell on that. I can bring in my notes from last semester when I taught this class and you can see, okay? But we're going to focus on the actual work, okay? And again, for most students, that work of just finding this antiderivative, finding that function as a certain derivative, that'll be sufficed, okay? Only if you're going really deep into math and whatnot later will that kind of build up with our limits and whatnot really come in any kind of contact with yourself, right? It's really just kind of this stepping stone just to make us jump through those hoops to see that process done, okay? But our main focus, again, if you go back to your chapter 3 notes, looking at all the derivatives that we had memorized from 3.1 through 3.4, 3.5, right? Thinking about how we differentiated, that's what's going to come in handy as we start to look at this section, okay, going backwards, thinking about, okay, how can I build this function that has a certain derivative result, okay? All right, so with that said, I'll leave it at that for today. Tomorrow, we'll do our introduction to chapter 5 and see that work and get into that notation business, okay? All right, Cruz, thank you very much for coming through. I'll put those notes up. Again, I did have the notes from yesterday. I posted those this morning right before our class started, so there was a delay there, but they are present, and I'll try to get these up later this afternoon as well, okay? Right on, thank you very much. Take care, everybody. If you have questions, stick around. Otherwise, see you tomorrow, same time.